Okay, let's start. So we are in Computer Science 101 class. We will be talking about during this course. It's more like, I don't know if you have seen, Harvard University has this CS50 course. It's free and online. It's kind of this that course which we will talk about everything, but not in detail. We will cover topics like programming in Python, functions and stuff, and also network. And at last, we will do some small backend programming, also some scripting with SQL and databases. I think what we haven't done with the previous class, we didn't cover a web. In the previous class, we didn't cover the web and HTML, CSS, and JavaScript, such topics, but with you, we will also cover them. But I don't know what kind of background each of you have. I don't know if you know counting in binary. I don't know if you know what is CPU, what is GPU, what is RAM. So first, let's do let's do small question and answer in those topics. Now, so all of you have computers, and those computers have some parts, right, which they work together, and you can do whatever you want with them. So they have parts like CPU. Anyone knows what CPU stands for? It stands for Central Processing Unit. It's actually the brain of the computer. Mother plate? No, a mother plate is a place like where all these components are located, and so that they can interact with each other. So we have CPU. I'm deleting this one. We have CPU, which is Central Processing Unit. What it does, it just compares stuff, adds, subtracts, I don't know, multiplies, divides. It just does basic mathematical operations. And it also fetches some data from your storage and also, I don't know, stores something in your storage. We have two kinds of storage in our computer. One is what yes, I don't know how to like as humans we have two kind of memory, like long-term and short-term memory. For example, you can give me your phone number and I will memorize it for some time, and next time I sleep and wake up I will forget it, but I will never forget my name, hopefully. But this is my kind of long-term memory. Also, computer has this kind of memory, like division, short-term memory and long-term memory. They do work with short-term memory because short-term memory is fast, but long-term memory is very slow for CPU to work with. So we have short-term memory is RAM. It stands for random access memory. Let's call it short-term memory. And the reason why it's called a random access memory, it means that there isn't any like order or something to access the memory. You can randomly go anywhere in the memory and get some data. It's random, like there isn't any order that fetch this one if you want to fetch the last one. That's why it's called random access memory, and it's probably called this way because of historical reasons. You know, in computer science, like whenever someone calls a term first time, then it actually goes that way. Like no one changed it. For example, I can give you an example. Like we will talk about HTTP, but there is there is this word that this is called HTTP header. Actually, this word is not right because we should have two R here. But no one changed this because, like, if you want to change this, you will have to change the whole internet. Like everyone uses this word. Like in computer science, like there are some words that once someone states that, it stays that way. Okay. Random access memory is short-term memory, and CPUs generally work with those memories because it's very fast to get data from it and also to put data to it. But we also have long-term memory, like we can use hard drives, we can also use solid-state drives. We have HDDs, we have like hard disk drive. It's actually a disk that actually spins. I don't know if you have seen, you've probably seen HDD, like it's something that spins, and in order to get data from there, like this arm should move and this like it's not random, right? You can't just directly go somewhere and get data because this arm needs to move somewhere and this disk needs to move, and in this way you can fetch some data from it. How it works, it's a little bit like like it's another topic of some degree, like electrical engineering. Like it works with magnets because magnets has two sides, like north side and south side. Like you can say north side is 1, the south side is 0, because we are all working with 1 and zeros. These are hard drives, these are old, and these are very slow, actually very slow, and because CPUs are really getting very fast, but hard drives are slow. That's for that reason we have another new technology called SSD, and this stands for solid state drives. SSD is like if you have like flash card, it's also using this same technology as SSD. It's sort of like RAM, where you can just randomly access any point and fetch the data. But in HDD, you actually HDD have moving parts, right? In order to fetch data, you have to do some spinning, like physical work. You need to do some physical work. But in SSDs and in RAM, I don't know how it works detailed, of course, because I'm not some kind of electrical engineer, but like you give some electric there and there are some circuits, and it gives you back some voltage, and you know that it's 1, for example. So these ones are these ones are long-term memories. So we have short-term memory as RAM. We also have another processing unit which does calculations. We call this GPU. It's called graphical processing unit. It's also a brain of computer. Like GPU and CPU, they do the same thing, but GPUs are really, really good at doing parallel works. Because of that reason, they are really good for like graphics work. Maybe you play a game, and like games are really just I don't know if you know about matrices, not the movie, like matrices in the math. Like you multiply them, I don't know, you multiply matrix to the vector, and there are a lot of these mathematical operations that happens when you play a game, and those operations need to be in parallel to be really fast. They are done by GPU. GPU does the same thing as CPU, but GPU does a lot of them in parallel. But for CPU, we only do some programming task, add and I don't know, remove and read something from the disk, and that's it. Okay. So my question is, like, do you have any question regarding to this one? Okay. So my question is, do you know binary notation? Like if I give you a number in decimal notation, like 10, can you convert it to binary notation, to ones and zeros?
To 1, 2.
Yes. We can do a quick recap of that, just to make sure that everyone knows. We are on the same page. Just let's start from the decimal notation. Okay, we have 543. How do we know that this is 543? Because this is 5 multiplied by 100 plus 4 multiplied by 10. Also, okay, 4 multiplied by 10, and also 3 multiplied by 1. Okay. We call this 540 and 3 because of this. So we have 5 hundreds and 4 tens and 3 ones. And if we convert it to like exponential notation, like this is 10 to the power of 2. I write this power of 2 like this because I don't know how to write this stuff. We can also do this 10 to the power of 2. We can also have 10 to the power of 1. We can also have here 10 to the power of 0. Yeah, actually, this is the reason why we call this 504, 543. Okay, because the reason why we have this 10 here, because we are in base 10 system. In base 10, what we have 10 digits, 10 digits to make up these words that we call numbers. What are those 10 digits? Everyone knows, from 0 to the 9. As soon as we if I want to count from 0 to 10, like I start from 0, I end to the 9. In the 9, I don't have anything to do. I either can go to the back, but also I can add the second number to the front. Let's write it. Okay, let's say I want to count to the 9. If 9 ends here, I need to continue counting, right? What can I do? I will just add another digit in front of current digit. Okay, it will be like this. So it will be like this. Okay. When we start counting, it will be 0, 0, 0, 2, 0, 1, 0, 3, 0, 4, and 0, 9. And as soon as we end with current digits, we add another digit to the beginning, and we start counting again from the 0. And last we have this 19, and then we add 1 to it and go like continue counting. The important thing to notice here, always we start from 0 and stop at 9. As soon as we are done with current sequence, we add another digit to the beginning, if we are done actually, and because we will be done in the hundreds, right? We will add another digit in the 100. The binary notation works exactly the same as the base 10 notation. The only difference is that in base 10 we have 10 digits, right? In base 10 we have 10 digits to make up some numbers. But in base 2, what we have 2 digits. We have 2 digits. We have only 0 and 1. The reason why computers only work with zeros and ones, because there are some physical stuff that in the nature that we can represent with 0 and 1. For example, I can send you electrical signal, I don't know, 50 volts, I don't know, volts, I'm not good at physics, volts, and if I send you more than 50 volt, we agree that it's 1. If I send you less than 50 volts, we agree that it's 0. And I keep sending you this data, and at the end you have like long sequence like 1 0 0 0 1 0 0 0. And in the computers, everything is represented with those ones and zeros. Okay, let's say we have what we have. Let's say we have some binary digit like this, 1 0 0 1 1 0 1. Let's say we have this binary digit. How we can represent it in decimal, we will start counting. What did we do here? Let's say we have 10 to the power of 0, 10 to the power of 1, and 10 to the power of 2, and we multiply this digit in this place, right? And we start counting from right to left, like 10 to the power of 0, 10 to the power of 1, and 10 to the power of 2. And we multiply it like 5 multiplied by 10 to the power of 2, 4 multiplied by 10 to the power of 1, 3 multiplied by 10 to the power of 0. We do the same thing in the binary notation. We will start counting from 0, 1, 2, 3, 4, 5, and 6. If I want to represent like see this number, what will I do? I will do like this. So 1 multiplied by 2 to the in the base 10 we have our base is 10. That's why we like multiply multiply by the multipliers of 10. In base 2 we have only 2 digits. Our base is 2. That's why instead of 10 we will have 2 here. So 1 multiplied by 2 to the power of 6, 6 plus 0 multiplied by 2 to the power of 5 plus 0 multiplied by 2 to the power of 4 plus 1 multiplied by 2 to the power of 3 plus 1 multiplied by 2 to the power of 2 and plus 0 multiplied by 2 to the power of 1, yes, 1 and plus 1 multiplied by 2 to the power of 0. Okay, this is actually what we will do to convert this number. Okay. And because when we multiply it by 0, we will have 0. Now we actually can skip these zeros here. Just I can remove these zeros. The terms which we multiply by 0 from the equation, I will remove them. So we only have ones. So we can calculate this. We will have and we can also remove multiplied by 1 because anything multiplied by 1 we will have the same number. I will also remove multiplied by 1s. What we will have here, we will have like 2 to the power of 6 is 64. 2 to the power of 5 is 32 and 2 to the power of 64. Yeah. Domain. Okay, I didn't calculate that fast. Okay, we have 8 and we also have 4, we also have 1. So what it makes is we have 74, right? We also have 78, 79, right? Correct me if I'm wrong. Okay, that should be. Okay, this is actually how we convert from base 2 to the base 10.
I can confirm, but my first answer is 77.
77. Okay, did I add anything? Okay, I had 2 more. Okay, you're right. Because when I added 64 to the 8, yeah, I added 2 extra numbers.
64 plus 17.
So what did you get that part? Shouldn't the sum of these numbers equal to that number? Is 7 digits?
This number?
Yes.
And yes, so our take from here is that this number in binary notation is 77 in decimal notation.
Okay, when we convert from binary notation to the other notation, we shouldn't get the same number.
Yes, we shouldn't get because we already have this number. Like we don't need to get this, but I can show you the way. I understand your question, but like doing this, we will always get in base 10. I was just showing you how to convert from base 2 to base 10.
A little question, why did you use exactly 2? Like 2 to the power of the number?
because we are in the base 2, we need to use 2 as our base. In base 10, we used what did we use? We used 10 as our base, right?
Yeah.
10 to the power of 2, 10 to the power of whatever. In this one, what do? We get our base as 2 because
Because we have only 1 and 0.
yes,
Okay.
yes.
Okay.
And as for your question, we also get the same number here. No matter like both of them are in decimal, but we also get the same number. I was showing this just to show you that this is actually how this is the same thing in the decimal. Also, this is the same thing in binary. In binary, when we start to count, what we get, like let's say we have only 0. Okay, we start to count from 0, and next we have 1, and we are done with digits. I don't have any more digits. So what did I do with 9? I added 1 digit to the beginning when I had 9, right? I will do the same thing here. I will add 1 digit to the beginning. It will be like so, right? It will be like so. If we continue counting, we will have this 1 1, and as you see in here, like this is where I was done with 1 digit. Also, I'm done here with 1 digit, so I will need to add another one. So what will I have? 0 0 and 1. Let's do it like this. Okay, this one, and in this way, when I continue counting, what will I have? Like 1 1 0 1, and then 1 1 1 0, and then 1 1 1, and then I'm again done with the numbers. I will have to continue adding new bits. So this is actually how we count with numbers. How we count in binary. And the one thing I want to mention that we might have, like you might hear a lot during in binary notation. For example, when we buy computer, we hear terms like is the architecture's 32-bit, like 64-bit. We have such stuff. And what it means, like, let's say we have only 3 bits, like 3 places to store bits. We have 3 places. I can only store 0 or 1 in any of them. What's the maximum number that I can have in these 3 slots? I have 3 slots like this one. Like this one. What's the maximum number I will get if I only use 0 or 1? Yeah, maximum number is this. So if we convert it to the decimal, actually this is 2 to the power of 3 minus 1. 8 minus 1, 7, right? 7. This is 7. If I have 3 bits, the maximum number I will get is 7. If we convert it to the decimal, doing the same thing here, we will get 7. Okay. Okay, I think this is 4. This is 2, right? This is 1. Yeah. If we add them, then we will get 7. What's the minimum number I will get here? The minimum will be when I have only zeros. It will be 0. So if I have a 3-bit, let's say 3-bit system, the maximum number I get here is 7, which is 2 to the power of 3 minus 1. If I have like 32 bits, the maximum number I get here is 2 to the power of 32 minus 1. The minimum number I get here is 0, of course, as always 0. Like if I have 8 bits, it's 2 to the power of 8 minus 1, which is 255.
How did you get number 7?
Number 7 from here, or
Yeah.
From here, if I want to convert this binary number into decimal number, what will I do? Let's do the same thing that we were doing before. What will I do? 1 multiplied by, okay, 1 multiplied by 2 to the power of 2, which is 4, okay, plus 1 multiplied by 2 to the power of 1, which is just 2, plus 1 multiplied by 2 to the power of 0, which is just 1. So we will have 1 plus 2 plus 4, which is 7.
So we are doing the same method that we did.
Yeah, yes. So this stuff was about like if I have only 3 bits, the maximum number I can get is only 3 ones, right? 3 ones are always like if we have all ones in binary, it's always like some power of 2 minus 1. It's always like that because power of 2s are really always represented like this. For example, this is 8. This is power of 2. Like 0, 1, 2, right? This is 4, okay. And this is 4. If I have this is 8. If I have this is 16, right? 0, 1, 2, 3, 4. Like 2 to the power of 4 is 16. If I subtract 1 from it, I will only have like all ones, 4 ones actually. Like if I have 5 zeros and 1 1, if I subtract 1 from it, I will get all ones. Like if I have 10, I subtract like if I have 100, like 1,000, if I have subtract 1 from it, what I get, we don't get this because we will subtract 1, we will get 3 nines, right? It's same in binary. So if I have like let's say 10,000, it's not 10,000, it's 16, but if I subtract 1 from it, what will I get? Only 4 ones. Okay. Okay, let me remove these parts. Do you have any question regarding to this?
Why do we need to subtract 1? Or you gave the example?
I was just giving example because we will we had here like what we had here. If I have 3 bits, what I was doing 2 to the power of 3 minus 1. If I have
Y minus
y minus 1, it's good question. With only 3 bits, I can only the maximum number I get is what? 7, right? Why I don't have 8 here? Because we've started counting from 0.
Yeah.
We didn't count from 1. We started counting from 0. That's why I don't have 8 here. I only have 7. Like I can of course start counting. Let's do something like this. Let's say I only have 2 bits. Okay, 2 bits. The minimum number is this one. Let's say let's continue counting. I think it's done, right?
Yeah.
Yeah. So what's the minimum number here? It's 0, right? 0. What's the maximum number here? Yeah, yes, 0, 1, 2, 3. What's 3? Is 4 minus 1. So with only 2 bits, I have 2 to the power of 2 minus 1. What's this 2 here? This is number of bits in here. We only have 2 bits. I mean, we call just one thing. I don't know if I mentioned this, just 1 or 0, it's called bit. Yeah, okay. So when we have n bits, the formula here, just maximum number we can have here is 2 to the power of n minus 1. Okay.
It's the max.
Yes. The minimum number is always 0. Okay. The reason why we didn't get like 4 here, because we started counting from 0, right? 0, 1, 2, 3. For that reason, the maximum number we get is like given n bits, maximum number we get is 2 to the power of n minus 1. I will connect this part to our CPU. Like we have 32-bit, we have 64-bit. Okay. Do you have any question regarding to this?
Just didn't get how we can convert normal number to the visual image number. Like how we can get from 3, 11.
Okay. I haven't talked about this, so we can talk about this. Let's remove this mess. Actually, it's also easy. We will just divide by 2 and we will get them. Okay, let's say I have 3. Let's say I have 3. The easiest way, without even dividing anything, the easiest way to convert 3 like decimal into binary. This is in decimal notation, and we convert it to the binary. The easiest way is to do this is in binary, this is in decimal. To find like let's think about it. What's the nearest power of 2, which is to the 3? Like what's the nearest power of 2 closest to 3?
Well, 1 and 2.
2, yes. Nearest one is 2. Nearest one is 2. Yeah, right. So I can write.
Well, the rules say like 1, 2 to the power 1 gives 2, 2 to the power 2 gives 4. They're in the same.
They're just one number away.
1 unit between them.
Yes.
So which one? Why we're choosing?
Like let's say I have here. Okay, 3 was maybe not good example.
Yeah, I get it.
Let's draw this. I don't know, x-axis here. We have, let's say 7, right? 7. What's the nearest power of 2 to it? Like if we get from the left side, right? It's like, okay. Power of 2. I mean, the number which is power of 2.
2 to the power of 3.
2 to the power of 3. No, not from the right. Okay, I get you. It's 8, but not from the right, from the left. Okay, let's. Which is less than 7?
2 to the power of 2.
Yes, 4, right?
Yeah.
It's 4. Okay, 4. Okay, what do I need to add to the 4 to get 7? It's 3, right? And so I need to add 1, 2 here, also 1, 1, right? So this is power of 2 to the power of 2. This method might be complicated, but it's 2 to the power of 1, and this is 2 to the power of 0. So I can add these numbers as these numbers to get 7. So my final number actually will be 1, 1, 1, 1, 1, 1. The reason why is that when we converted from binary to decimal, what did we do? We did like 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2. I know it might be a little bit complicated, but I thought it might be a little bit easy for you, and just to think what's the closest power of 2 to the number you are given before yes, which is less than that number, right? And then in this way you can construct like the goal is to get this number by using only power of 2s, like 4, 2, 8, I don't know, 16. The numbers which are power of 2s. Like let's take let's take I don't know, 17, which is not all ones. What's the closest number to it? Yes, 16. What do I need to add to it? 1. So we'll have 2 to the power of 0 and 2 to the power of 4, right? So I will have, like, let's write here 0, 1, 2, 3, 4. I will write 1 here. I will also write 1 here, yet, and I will have only zeros in the middle.
What?
A nice question. Why? Because I only need to add 2 to the power of 4 and to the power of 0, right? I don't need this 2 to the power of 3, 2 to the power of 2, 2 to the power of, I don't need this, right? To get 17.
Okay, yeah.
That's why these middle numbers need to be 0. Because you remember when we removed zeros from here, we didn't use, because when I converted to decimal, I will actually multiply 0 by 2 to the power of 5, which is 0,
Yeah.
right? For the same reason, we don't need, if I don't want to get anything from here, I will put zeros here. I only need this one, or also this one. Like I only need power of to the power of 0, also to the power of 4. What if this was a 1?
Then we need to add.
We will have like, yes, 21. We will have 4 also. We will have 1, which is 21. Like, let's go to the right. What if I want to convert 21 to binary? What's the closest number which is less than
4.
yes, which is 16? 20. I can represent 21 by this, right? Which is 2 to the power of 0, 2 to the power of 2, and 2 to the power of 4. So I will also draw something here, which will have like 4 slots, maybe 5 slots, I don't know, like 0, 1, 2, 3, 4. Like 0, 1, 2, 3, 4. So I need only 2 to the power of 4. I need 2 to the power of 2. I also need 2 to the power of 0, because I will add them to get 21. The others I don't need. So I put 0 here. So 21 in binary, what is it? 1, 0, 1, 0, 1. Is the idea is clear?
Yes.
Like you need to get this number by only using power of 2. If you understand like decimal and binary, like there might be like infinite number of number systems. We have hexadecimal notation, which is base 16. We don't have 10 digits, we have 16 digits. Like we have base 8. It's also called octal. Like we don't have 10 digits, we only have 8 digits. Like you remember when we stopped in the 9 and started counting again?
Yeah.
In base 8, which is octal system, we stop at 8 and start again. Like we only have 8 digits, or 7. Okay. This is like, if you understand this only binary and decimal, like all of them would follow, because we might have like infinite number of number systems. Like someone also created base 600 something, I don't know, like 6500 something, I don't know, someone created this. In this number system we have like 6500 and some digits. In now base 10 we have 10 digits, in this base 65 and stuff, and we have this number of digits to make up some words. For example, English alphabet is like base 60, what? 26, yeah, 26, base 26, because we only have 26 letters to make up some words. Okay.
And I have a question. In that two-system base, we're using only 1 and 0. In this case, can we use another numbers for example, like 5 and 4.
No, if
Like,
you
the meaning is going to be same, like we're going to use like a symbol. I'm not saying exactly the number, but can we use the symbols?
yes, we can use. You can create like your own number system. I don't know. You can teach your girlfriend this, and you can chat in this number system, and no one will know
Yeah.
how to convert. Only you will know.
Okay, so like computer science, they picked 1 and 0 only because they're close to each other, the like beginning, but they could choose another symbols.
Yeah,
Theoretically.
yes, they could in computers because like the 1 and 0 we can like represent them in like nature, right? For
Yeah.
example, I gave example from electrical signals. You might have like some high voltage or low voltage. Like you can call one of them 1, you can call another 0.
Yeah.
And you can make up these words like long strings of characters from this. And I can keep sending this electric to this guy, and he can know that I am sending 100001111001100, and he will decode and he will know that I am sending like some number to him. Yes. So the other way to convert from decimal to binary is just to divide by 2. Like if I want to convert 21 to base 2, I will divide it by 2. What I get is 10, right? Actually, well, what we are interested in the reminders of the division, not the no, not the result. What I'm interested is the reminder. If I divide 20, let's okay, if I divide 21 into 2, I can get 10, right? And what's the reminder I get here is 1. 1. The 1 is my reminder here. How can we? Okay, I think I made a mistake here. Because 10 will be okay. I didn't actually. Okay, if I divide 10 to 2, I will get 5.
And if you don't have a reminder, then it's 0.
The reminder is 0. The 5 divided by 2 will be 2, and I will have a reminder of 1. And 2 divided by 2 will be 0, and I will have nothing left. At the end, I will have 1, and I will write this 1 here. So this is my number in binary. This is the same number that I get. But be careful, because this number is reading exactly correct from right to left and left to right. But if I'm not mistaken, we will need to read it from like right to left. I'm not sure, but you can just try your own numbers at home.
Yes, it might be from right to left.
Yeah, yes. The reason why we get same number, because like it reads same from right to left and left to right. Okay, so this is it. This is how.
Second method is easier than the first.
Really? Maybe.
It's more simple.
Yeah, it's simple, but yeah, if you want to do it in your head, like without dividing, I don't know, I can't divide in my head maybe, but for me, maybe it's easy to find the powers of 2, because like most of them are really common in everywhere. Like for example, 128, I think it's 2 to the power of 7, I believe. Like for example, when you buy a computer, you have like storage 512, like it's also power of 2. So these are common, so you can actually remember some power of 2s. Okay. Okay. So this was just crash course on number bases. Let's return to our computers. So what CPU does? CPU is we won't talk about this GPU stuff. Like it's another topic. Like it's some topic in computer graphics maybe. So CPU is we said central processing unit, which just does calculations, compares something, does calculations, gets something from memory, and that kind of stuff. Because we will talk about programming, maybe not in this lecture, maybe in the next lecture, but we will talk about programming. So what we have here, my question to you is, what is program? In your own words, what would you answer if I asked you, what is a program?
Program or programming language.
No, just program.
Like it's Latex says like
So I can say that we need program to solve problems.
Yes. And to solve problems, you need some steps.
Latex says like somebody said you have to do this.
Yes, like commands.
Yeah, commands.
Like commands. So the program is just a list of commands, which we also call, like CPU vendors call them instructions. Like each CPU has their own instruction set, which means that you know what's set, right? It's just set, which have only unique elements. Instruction set is just instructions that this CPU understands. For example, I have, let's say Mac, which use M1 Pro. It has its own instruction set that I can give it some instructions and it will execute. For example, it might have instruction called add, which will add two numbers, for example. It might have, I don't know, instruction called call, which will call some function, I don't know. For example, it might have instruction called move, which will move some number from my memory to the register, which I will talk about it. Okay. So the point here is that a program is just sequence of instructions. What CPU does with those instructions, it just it gets them and I don't know, calculates them, and like CPU, what it does, it gets something from memory, calculates it, and puts it back to the memory. Okay. I have Firefox open here. Firefox is a program, which we said it's sequence of instructions. When I open Firefox, what happens? I actually downloaded Firefox to my disk, right? I have HDD here, and yes, SSD actually. I have SSD here, which is long-term memory. Whenever I close my computer, turn it off, it actually stays there. I have SSD. Let's draw this somehow. I have here SSD, and I have, let's say here, Firefox. Let's maybe make it interesting. I have here Firefox. This image is too big, but yeah. Okay, hopefully it will get this. Okay, I have this Firefox logo here. Okay, I have Firefox here, which lives in my SSD, because when I bought this computer, I downloaded it and installed it on my system. It's permanently on my SSD, like unless I delete it in my I decide to delete it. I also have my CPU here. Let's call CPU. And let's also decorate it a little bit. CPUs sometimes are decorated like this. Not good at painting CPUs. I also have my RAM, which is RAM was like short-term memory, right? Okay. I have the SSD here, which is long-term memory, and as we said, it's slow. and it's not slow, but it's slow for CPU to go there, fetch some data, and it's like, for example, let's say you have some bookshelf. You can just go there and fetch some books. You also have some library, and I don't know, on the another street. To fetch some book, you need to, I don't know, leave the building, go there, and get this book. That's for that reason it's hard for CPU to go that long way to fetch this on, I don't know, just 1 bit or byte. That's why when I start a program, when I open Firefox, it will be loaded to my RAM, because my computer is preparing to run to it. For this reason, my computer will load it to my RAM, because for CPU, it's really fast for it to work with RAM rather than work with SSD. Okay. And then what will my CPU do? I don't know. Will ask for some data. I don't know. Will do something and return, write something back to the RAM. Like it will be like get some data from RAM and calculate it, write back it to the RAM. It will be same stuff. Happening a lot during, I don't know, 1 millisecond. Is this clear? Like high level overview how this works? Okay. That's why we actually need RAM. For example, I might have 16 gigabytes of RAM. Okay, I might have, let's say I have 16 gigabytes of RAM. Let's say 16 gigabytes. We didn't talk about gigabyte, megabyte, but we can talk. Honestly, I don't know them by heart, but I can show you. Okay, let's say Firefox only uses 4 gigabytes of RAM. When I load it to the RAM, actually I have to load it to the RAM, because when I click Firefox, it will be automatically loaded to the RAM. Why? Because for CPU, it's easier to work with RAM. Okay. If I have 16 gigabytes of RAM and this Firefox uses 4 gigabytes of RAM, what will I have? I only have 12 gigabytes of RAM to work with. And what the CPU does, we will zoom into CPU part to talk about this. But basically, what happens is just this. What happens when we run a program? It's just this. We load this to the RAM, and CPU does something with this memory, with this data. Okay, if you want, we can just have just 5 minutes break if you want. I don't know if you go to smoking or just some fun, or we can continue. Do you want to have break?
Yeah, sure.
Okay, let's just process this information. Okay, we have like high level overview of like what happens when we run a program. And actually all our programs are stored in our SSDs, because we don't want to lose them. We can lose them, but if we crash the SSD somehow, but yeah, whenever I open any program, not just Firefox, I can open any program. We will write programs in Python. They are also a kind of program which we will save on our disk. But when we run them, actually, our operating system will load program to our RAM, so that CPU can work fast, really fast. Actually, a program might use some memory, as for example, Firefox, let's say it used 4 gigabytes of memory. That's why our RAM actually, like, the larger the RAM I have, I can have more programs run simultaneously. Like let's say I have only 2 gigabytes of RAM and my Firefox uses 3 gigabytes. Like it will work, it will still work, but it will work very slow, because it will use 2 gigabytes here and it will use 1 gigabyte from my hard disk, and there will be some latency, right? it will, I don't know, freeze sometimes. There will be some latency. When I click, I will have some late feedback. For example, if I click something, it will work a little bit late. Now, that's why the larger size RAM I have, the more programs I can run parallelly, simultaneously. Like I can play the music, I can listen to music, I can play video, I can write code, and all of them are actually one program, and those programs take up some space in memory. That's why, like, we have this main memory, this RAM. We store all currently running programs are all stored on RAM. Okay, this is it. I can actually, like in Windows, on Mac, on Linux, they are different, but let's say I'm using Mac, I can go to activity monitor here. I can see actually how much memory my programs use. For example, I'm using Firefox. Firefox use like 900 megabytes of memory, approximately. Like Zoom uses like 347 megabytes. Also, just to mention about megabyte and gigabyte, what is a bit? It's 0 or 1, right? What is a byte? It's 8 bits, right? Bit is 0 or 1. Byte is 8-bit. Okay, and when we have 124 bytes, we call this a kilobyte. When we have 124 kilobytes, we call this a megabyte. When we have 124 megabytes, we call this a gigabyte. When we have, like it's continuous just like this, when you have 124 gigabyte, we call this terabyte. And when we have 124 terabytes, we call this petabyte. Actually, the list continues. Like we have, I don't know, zettabyte, yottabyte, petabyte, and we have actually petabyte here. Like they have a lot of terms to represent this memory. Okay.
Why exactly 1020?
I'm not sure. As you know, it's power of 2. Probably it's related with like in memory I can only store 0 and 1, right? And if I store like 8 bits, it means the maximum size I can have, like what's the maximum, like because of only zeros and ones, because of this base 2 system, I always have some power of 2. This doesn't necessarily have to be 120 bytes to be 1 kilobyte, because this is something defined by scientists. And for example, if let's say I am a scientist and I call 1 kilobyte, not 124, I just actually 1024. I don't want to call it 1024. I want to call it only 1000. It's something defined by just people. And I'm not sure exactly the reason why it's called.
I just calculated because 2 to the power of 10. Maybe that's why.
Yeah, yes, this actually the reason is because all of them are power of 2s, but like they could only just call 1000 bytes is 1 kilobyte, right? They could say that, but they didn't, and I don't know why they did. Probably, I don't know, maybe because it's easier to calculate. I don't know, easier to memorize. Actually, it's for me, it's not easy to memorize, but anyway, yeah. Okay, if we zoom into the CPU part, what CPU has? It has its own like small memory address. We call them small slots, which also serves as some memory. Okay, let's say what we have here. We have a CPU. We have a CPU. It's our CPU. And CPU has some small memories, which is like which is not as far as RAM. They are very close to CPU. They are called registers. Like let's say I have one register, I have two register, I have three register, and I have four registers. Let's I don't know how somehow align them. I have okay. I have four registers. We call them registers. These small memory units are called registers. What we do then, we just store some temporary values there. Let's say I want to add two numbers. I will store two numbers in two of them, and whenever I added them, I will store the result in another one. And if I want to store the memory, store it back in the RAM, I will call some instruction that it will send it to the RAM. Okay, these are called registers. And in modern CPUs, registers can be, for example, 32-bit or 64-bit. Let's say our CPU is 64-bit architecture. Like whenever you buy a computer, it's like it's written somewhere in the specifications. I don't know. It's either 64-bit or 32-bit. It's always like that. And the meaning of this 64-bit or 32-bit is that it denotes the size of the register, size of a single register, how many bits a single register can hold. For example, if I have 64-bit architecture, it means my CPU has 64-bit architecture. It means that it has registers that can hold only 64 bits, which means that can hold maximum number, which is what's the maximum number? 2 to the power of 64 minus 1. Like we had 3 bits, maximum number was 2 to the 3 minus 1, right? Yeah. And for 64 bits, maximum number is 2 to the power of 64 minus 1. It's actually very, very large number that you don't really need to worry about. But like it's having 64 computer, like 64-bit CPU means that registers can hold that large numbers.
So it's better to have the computer with a 64-bit architecture.
It's good actually.
Because it will be able to solve at the same time more problems.
No, at the same time, like is another topic. It's called like they might have several cores, but I will come here. This only means that it can hold, these registers can hold large numbers, and for that reason, we can have calculations on large numbers, not just small numbers. Let's say I have 32-bit, right? What's the 32? Let's calculate what's 32-bit. What's the maximum number that I can have with 32-bit? Yeah, it's actually this number. Like I can't, if I have 32-bit architecture, I can't have like larger numbers than this. Of course, they can have, but in order to have larger number than this number, they will have to do some complex, I don't know, calculations. I don't know how, but having 64-bit, it means that like you can have a really, really large number. It's like compare this number to this number. It's clear. Okay. So let's say I want to add two numbers. I want to add two numbers. I need to write a program to add two numbers. What was a program? It's just a sequence of instructions. Each CPU has different instruction set. Well, like we might have different CPU vendors, right? For example, Intel is CPU vendor. We have AMD, another CPU vendor. We have M1, I don't know, Mac, like Apple has its own CPU, which is called M1, M2, I don't know. For example, for mobile devices, we have like Snapdragon, don't know. Like we can have different CPU vendors, and to give them commands, like each of them have different instructions. Like you can't give the same instructions to each of them. All of them speak different languages, like you can say that. Okay, if I want to add two numbers, like I will have some program like this, for example. I will just write it. Let's say my program says get I don't know, store number 5 in, let's say actually number this registers, let's call them, I call this AX, BX, CX, DX. I give my registers just a name, okay? I just name them so that I can remember them. Okay, if I want to write a program, I will work with only those registers, okay? First line of my program says that store number 5 in AX, okay? AX. Maybe write it somewhere here. Just a minute. Let's call it CX. Let's call it DX. Okay. I will clear them so we can write something into them. Okay. This is my program. I give instructions. Store number 5 in AX. I give it to CPU. CPU stores number 5 in AX. Okay. My second instruction is store. Okay. Add a number 10 to AX. It means that get whatever in here in AX register, add 10 to it and store it back in AX, for example. And we get 5, we add 10 to it, we get 15, and like this. We can also say, for example, load, for example, some variable, I don't know, some value from RAM. I don't know, load some value from RAM, don't know, and store it in RAM to, I don't know, BX. We can also call this like this. Load some value from RAM to BX. I don't know, maybe we have in RAM, we store some large number. We get, CPU will reach to the RAM. We'll get this number from RAM and we'll store it into this BX register. I don't know, this number. Okay. Then we can like continue doing some calculations on that. Of course, we might have like different instructions and different. This one is actually in English language. This is a program written in English, but we can write them in more like less understandable way. For example, mov 5. I don't know, to AX, I don't know, add AX 10, I don't know, that's 5, then load, I don't know, BX. Like in real computer language, in real computer instructions, this might look like something like this. Move means move, I don't know. Add means add, subtract means subtract. And by writing a program, we actually write these instructions. Okay. I can show you some examples. For example, I will go to Compiler Explorer. I will write Compiler Explorer. We'll have some examples here. For example, what do we have here? Okay, look at this code, I don't know how to move them. Is this maybe just look at this number, like look at this code. Is this somehow like, can you explain it, even if you don't know this programming language? It's some code written in C++. It gets a number which is an integer. Integer is just like integer. It's not, it doesn't have decimal places. It gets a number and multiplies the number by itself and returns back somewhere. Okay, like in computer language, it will be something like this. Move something from somewhere. I don't know how to call it. Maybe let's call this function. Okay, I don't know what happened here. Maybe let's use another language here, which is more clear. Delete this. I will have here var x5 and var y is 5 plus 10. Maybe we can. It doesn't work correctly, maybe. Does it work correctly? Compilation format or whatever. I just want some example, not. Okay. Do we have Python here? Yes, we have Python here. Okay. Okay, it's the same thing, right? It gets a number and multiplies it by itself and returns. Okay. These are some sort of CPU instructions like load const. It means load some constant, which is just a variable. And what happens if I call this again? I don't know if probably it will work. Okay, it works actually. Maybe I can directly just x equals to 10 plus 5. Okay, it works actually. Okay, 10 plus 5 load const. Yeah, it actually directly added 10 to the 5. Maybe a equal to 10 equals to. Okay, let's look at this one. We have a load name. We create some name and store 10 in that name. We call this variable, which might change. Then we have stored name x. What is x? X is a plus 5. I want to say like this is this line, right? And this is this line where we have a plus 5 and we store the value in x and we return this value, I don't know where. Yeah, like I don't understand all of them. Also, I don't want you to understand them. But like the idea is just to see what a program does. A program is just a bunch of instructions we give to CPU, and CPU executes them. How CPU does it? It's really complicated stuff. I don't even know detailedly. Like it's just a bunch of circuits connected to each other. When you give some voltage and it lights up the others, and at the end you get some electrical signals that you know that this is addition of some numbers. So basically a program is just like instructions we give it to them. For being really fast, CPU has some registers which is close to it, so it doesn't have to reach out to the random access memory every time to get some value. Okay, is this just idea is clear? Okay. What is RAM? RAM is just RAM is like how can we say? It's like a table. RAM is like a table. RAM has like slots, and in each slot we store some value, some number. Yeah, we can store anything. We cannot store anything else. We only store numbers because computers work only with numbers, right? Okay, so our RAM is actually a table with two columns. On the right side of the column, we call this address. Actually, this was left. Left side is address and right side is value. Each value stored in RAM has its own address. Okay, address might start from 0. For example, let's say 0, 1, 2, 3, 4. Sometimes the numbers are written in hexadecimal, which means base 16 notation, not base 2, not base 10, but base 16 notation. When people write in hexadecimal notation, they write number x. For example, 0x0 means just 0. 0x1 means just 1. 0x2 means just 2. It's just 1. Okay. Okay, these are my addresses, okay? And in each address, I might have some values. For example, let's say I have here some, this value, I don't know, in this address, I have here some value in this address, I have some value, I don't know, value in this address. When we actually, for example, in CPU, if I say load some number from RAM, I don't know the number. CPU actually just goes to that address. For example, I can say that load 0x2 to bx. I mean, whatever in this address, get this data and store it in my bx register, for example. Okay, idea is clear, right? Each of them has address. When CPU wants to fetch some data, it will refer to them by its address. Okay. Okay, that's it. And the reason why CPU only work with its own registers, because it's easier for it to fetch some data and store some data to there. When it's done with this data, it will write them back to the RAM. For example, let's say I have calculated it and I want to store it into RAM. For example, I can store it, I don't know, 0.3, for example. Store whatever in bx register in this address, for example. And when we say it to CPU, it will clear it and it will come to here and write this, whatever was in this register. In programming language, we have some stuff that we call variables. Variables are just these addresses. For example, you saw, right, my when I wrote some compiler explorer, let's say I have here, okay, open. I have 10 here. I have like this A is some address in RAM, and this 10 is a value of that address. Okay. And in programming language, we call them variables because it's just something that can change. Its value can change. That's why we call them variables. Okay, and then we can do some calculations on them. We can print them. Print just means that just show me the value. When you call print, it's I don't exactly know what the CPU will do. Probably there is some instruction called print for CPU. You call it, and it gets, I don't know, gives instruction to somewhere else. For example, GPU, and GPU shows that data in the screen. Okay. Do you have any questions regarding to anything we talked about today? I don't know, maybe something not clear because I didn't explain it very clearly.
It's good.
Sorry.
It's clear.
It's clear. Okay. Okay, for today, I want to switch to the programming language. I tried my best to explain what is a computer and what is a program. I hope it's really clear. So we will during the whole course, we will write programs. So that there are many programming languages. Why do we have programming language? Because we don't just want to work with CPUs, because it's really hard to work with CPUs. Let's say add two numbers in Intel CPU. Let's see how can we add two numbers in for Intel CPUs. Okay. This is probably, yeah, maybe this, I don't exactly know which of them are correct, but let's say. In order to add two numbers in CPU, I need to write all this gibberish, which is not like, even if I made some mistake here, like I will have to debug it, like, I don't know, I will have to research it, why it happened, where it happened. But actually, it's clear that it's just instructions. For example, move some number to register 1. I don't know. Increment number which is in register 1. Add number in register 4 with some register 1. I don't know. Move some stuff to some place. It's just instructions. But for humans, for programmers, it's really hard to work with CPU instructions. And also, we have many CPUs. Like I said, many, like we have hundreds and billions. I don't know, like we have different CPU vendors, right? We have, we even have CPUs in our phones. We have CPUs, maybe this, what's called projector. We have CPUs in our projector. We have CPUs in computer. Each of them have different architecture, and each of them have different instruction set. That's why for like hiding these details of CPU language, also being able to write some code, some commands that are close to human language, people created programming language. We do the same thing. We give instructions to CPUs, but we do it like human-friendly language. Which we call programming language. Is this clear? We have many programming languages like C. You might have heard this, C programming language. Like it's considered father of, I don't know, all language. It's not really father, but like there was also another programming language before this one. So we also have, for example, C++, which was released after this C programming language. We have Java, which is also another programming language. We also have PHP. It's very popular on the web. Someone wants to build a website, web application. They use PHP. We have also C#. We have Ruby. We have, I don't know, Python. We have, for example, Golang, which is popular today. We have, I don't know, Rust, which is very popular today. Rust.
R.
R, yes. We also have R, which is, I think, used very a lot in data science, right? It's used in data science. R.
As I know, it's really hard, and most of the people skate.
In university, actually, they taught us our programming language in some data science course that I actually didn't like it, but yeah. Python is way more easier. Like, I don't know, it's not really simple. Python is much more simple. Okay, for the purpose of simplicity in this course, we will learn Python, which is a programming language, which is really close to like human language and also simple. Like you don't have to write maybe 10 lines of code to do some small thing. Instead, we can just write 2 lines, maybe 1 line, and solve some problem. Okay. let's say I want to write program in Python and I want to execute that program. So I want to give this program to my CPU so that it can execute these instructions. My CPU doesn't understand Python. It only understands its own instruction set, right? So we need another program which will convert my Python code into CPU code, okay? We need another program. Let's say I will write in Python code. And on the right side, I have CPU instructions. CPU instructions. Okay, I need some tool that I want to convert this Python code into CPU instructions. And those tools we call compilers. Compiler or interpreter. You know what's interpreter, right? For example, let's say I'm speaking Arabic, someone listens to me and converts it in real time, converts it to English, for example. That person called interpreter. So interpreter is same as here. So I speak Python, it real time like converts this Python instructions to CPU instructions so that CPU can execute them. Compiler on the other hand, actually compiler does them ahead of time, like gets the whole Python code, compiles all of them into a bunch of CPU instructions and gives it to CPU, and CPU just look at instructions and execute them. Okay. Interpreter does it real time. For example, you say it, I convert, you say it, I convert. But compiler does like whole thing, like I finish speaking, then compiler converts, translates all of them and translates all of them to Arabic, I don't know, to English, and transfers it. And it's the main difference between compiler and interpreter. Interpreter does it sentence by sentence, but compiler, yeah.
Because it's fast.
Yes, but like it's some debate topic. Like you might have some debates, like some programming language is compiled language, some programming language is interpreted language. But at the end, everything gets interpreted because what CPU does is actually interprets, right? Move, I don't know, add, increment. Like it looks all the instructions one by one. At the end, everything gets interpreted. But like it's debate topic. Some people argue that some compiled programming languages are better. I don't know. Interpreted programming languages are worse. I don't know, but like it's debate topic. Okay, so we need some tool to convert this from this to this, right? For that reason, we will go to python.org and download that tool. If you haven't done this before, and you have done this before, okay, you can just go write download Python, which means download Python compiler, Python interpreter. Okay, you can just go to download Python, and we can download Python version 3.11.4. Like what's the latest version? Doesn't matter for us. You can do it right now. We have 15 minutes, but yeah, you can do it right now. Doesn't matter. You will just download it, and it will give you some setup, and you will click next. For Windows users, just make sure that there is some text there. It's called add something to the pass. Please check that. Let me Python Windows install. I don't know if we have some pictures because I don't have Windows laptop. Yeah, for Windows users, please check this one, okay? Add Python to the pass. Otherwise, you won't be able to use it directly. If you haven't done this, maybe, I don't know, I can help you to set this up, but
I'm actually not sure if I did. But right now, yes.
On your terminal, if you write Python, if it works, then it's fine. Let me check.
Let me open.
So I fixed that. It's just download and you just need to click on this and didn't install. What happened?
I did, it says installed.
So you clicked it open just folder or what happened?
Yeah, you just opened this.
Maybe yes. Let me. Let's download. You clicked on the download. So you moved to applications folder, right?
No. It didn't show this. It usually shows, but in this case.
Okay, let's open terminal and write. Actually works. Is it? I think you already have installed. I mean, you already have Python installed in your system. Okay. We will use Python 3. Like it's okay, it works. We will use Python 3. Okay.
And where is it? This app, it should be as an app.
Yeah, it's app that we will execute it. Have you ever worked with terminal? It's just command line, right? In Mac, I can write terminal. It will open this command line. Just I can write some commands here. For example, clear. I don't know. It will do whatever I say. For example, ls shows list of folders and files. It's just command. Have you ever worked with this? On Windows, it's different. On Linux, on Mac, it's different. Okay. Have you installed Python already? Yoksa yüklenir. İnternet sayfası evde ellersin.
Şimdi var böyle.
Let me see.
Hangi bir şey?
Yani bundan sonra diye komanda komand bunu son Windows terminal böyle saçma mesela komanda yazmışlar ls listing yapamaz. Bunlarda bak böyle user hem bakılımız vardır. Buna
Visual Studio.
orada işte. Çok da fark olmamalı. Yani orada 2-4, əsas orada 3-dən başlayırsa okey. Okay. So if you have Python installed on your system, then you can open terminal or CMD. I think you all know how to open it. On your terminal, if you write Python on Mac, you will write Python 3. On Windows, you just write Python, okay? But on Mac, you'll have to write Python 3 because we have 2 different versions of Python. Okay, if you write this and okay, I have Python 3 because I'm on Mac. If you write this and it gives you some output like this, it shows you the version of the Python that you have installed on your system, then you are totally fine. Then we can create some files. We will also need some text editor. I don't know, you have Visual Studio Code, right? Do you have any text editors? Like, okay. We can write Python programs on text files, doesn't matter. I can write it on Notepad, Notepad++, it doesn't really matter. But some text editors really help us to write Python code. They help us along the way, like when we write. And that's why we will use some of those text editors. I give you choice. You can download Sublime Text 3. I would prefer this one if I were you. We also have VS Code, which is Visual Studio Code. Please don't download Visual Studio. We need Visual Studio Code, okay? Visual Studio Code. And we also have Sublime Text. Just download any of them, doesn't matter. Okay. It's better download Visual Studio Code, okay? Okay. Can download Visual Studio Code if you don't already have it. Were you able to download Visual Studio Code? It should download. Is this Intel Mac? Right, it's 2000.
Yeah, it's kind of this one.
Okay, it will do the same. You will drag it to applications folder. Maybe because of the internet. What about you? Were you able to download Visual Studio Code? İnternet bizde yoktu. Okay, I will show you. Maybe you can We have still some time, maybe you will download, but I will show you what we will do. I will open Visual Studio Code, just empty app, okay? Don't mention this because I was working on something. Let me close folder. Not editor, sorry, close folder. Okay, when you open this, you will have some screen which will look like this. I don't know, you might skip some starter tutorials. If I want to, I need a Python file that I want to write some code in Python file, okay? Python files should always have extension .py, okay? We already know about extensions, right? For example, image might have PNG extension, I don't know, GIF extension, SVG extension. And so Python files will have extension .py. Whenever we will create a program, we will have some file name .py. So I will create a new file here, new file. It will be, let's call it text file, and I want to save this file. Okay, save as, or I just can click Ctrl S. I will save it in the desktop, maybe on desktop. I will call it main.py. Okay, main.py, and I'm zooming this. On your Visual Studio Code, as soon as it sees this Py extension, it will know that it's Python file and it will show you the logo of Python, and we can write some code here. As usual, every programmer, when they start their programming journey, they write hello world. So we will print hello world, okay? Just this line, print, and then inside the brackets, we'll write hello world, but we need to write it inside quotes. Double quote or single quote doesn't really matter. We can write double quote or single quote. It's okay. Then, after doing this one, I need to open a terminal. I will go to this terminal tab here. I don't need to switch to other window or something. Visual Studio has integrated terminal. So I will open terminal, and I have this main py file here, right? I will call my Python program, which I downloaded and installed, and I will give my program this Python file as input. This Python program will take this file as input, will convert it to CPU instructions, will execute them, and will show the output in the terminal. Okay, I just need to click enter. Yes, because I'm not in desktop, I need to go to desktop. My file was in desktop, that's why. Okay. I'm on desktop, and my file is on desktop, user or on desktop. So I just need to execute this file. To execute this file, I need to call Python through. This will show me hello world, and congratulations, we are a programmer and we can apply to Google now. Yüklenmedi. Okay. So this is it. So this is our first program. I will try to send you some maybe informative videos in English. It's good that you all know English, because I have had some students which doesn't speak English, not even Russian. So I had to find them resources in Azerbaijani, which doesn't exist. Yeah. I will try to send you some interesting videos that they have plenty of videos on YouTube. Okay.
So for any homework?
For now, not.
Just to download the labs.
Yes, for now, just try to revise the topics that we have covered, like try to convert some numbers from base 10 to base 2, base 2 to base 10. Don't know, just I will send you some videos, try to watch them. Also, just write this hello world. Just do these 3 things.
We're going to send all info to our group chat.
Yes, I'm sorry.
Okay, great. Next class is when?
Thursday. Yeah, today is Tuesday, it's Thursday. Okay. Okay, so this is it. We can conclude our classes. If Visual Studio Code hasn't been downloaded, just try to download it at home and try to execute it. And just make sure that you execute this command wherever your file is. My file is on desktop and I should execute this on desktop. If I'm not in desktop, let's say I'm on another folder. I'm this where I am in this folder and my file is in this folder. Okay, and then I need to provide the full path to that file. Okay, I'm in here. My file is in /desktop /main.py. This will result the same. Like you need to provide path to the file because Python needs to know where the file located. Okay, just make sure if you don't if I don't provide the correct path to the correct file, then I will have some errors like can't open file. Actually, it's quite clear from the error because we don't have such file in users or Han main.py. We have file on desktop. Okay, just try to reproduce this step at home and then I will see you on Thursday.